So the last form of separation that we're going to talk about, and our second form of ion separation specifically for this module, is capillary electrophoresis. Now, this is not a chromatography technique, but it is still separation. But here, separation is based on how ions are going to move in an electric field and be separated based on that movement. So if we have an electric field, such as the one created between the anode that is positively charged and the cathode that is negatively charged, what happens is your positively charged cations are going to be drawn toward the cathode, while your anode is going to draw towards it the anions. Okay, so we're going to get different movements depending on the charge of the analytes. So in general, if we were to want to observe the separation of these analytes, we would need to put two detectors down, one on either end, one to observe the cations as they come towards the cathode, and one to observe the anions as they go to the anode. But that's not necessarily a practical thing. So what we'll talk about today is how we can build this capillary electrophoresis idea into something that actually is going to allow us to do separation using one detector and being able to see both cations and anions. Okay, so let's break this down just a little bit. Okay, we're separating anions based on their mobility in an electric field. Okay, so there's some kind of accelerating force that comes from the force of this electric field, the strength of the electric field. Okay, so we have this QE accelerating force. And that's going to be kind of offset by a frictional force. Okay, now F here is the friction coefficient. And this mu EP, this is our electrophoretic velocity. Okay, and the electrophoretic velocity for a specific ion is just how fast is it going to move when exposed to a field of a certain strength. Okay, so here Q is our charge of the analyte in coulombs, and E is the electric field strength. Okay, so this makes sense. As we would increase the charge of the analyte, it's going to be more strongly drawn towards whichever end it's being pulled towards, and it's going to move faster to get there. But also, if we increase the strength of the electric field, there's a stronger pull, and we get a faster electrophoretic mobility, or electrophoretic velocity. Now, if we increase the friction of the solution that the analytes are in, that's going to make it more difficult for them to move. So as we increase the friction coefficient, we're going to end up decreasing the electrophoretic velocity. Okay, so all of these aspects play a role. So we want to be increasing the charge, increasing the electric field, or decreasing the friction coefficient to get our electrophoretic velocity higher and a faster movement of the analyte. But we can use how they move to distinguish between them. So obviously in analytes with similar charge under a similar electric field, if they experience different friction coefficients, they're going to move at different rates. Or if they experience the same friction coefficient and have a different electric charge, and have the similar electric field, they might separate and have different velocities based on their charge. So charge is one way that we can separate them out. Now, what does this friction coefficient do? Like, what goes into that? So into the friction coefficient, this is 6 pi, the velocity of the solution, and the hydrodynamic radius, or viscosity, not velocity, viscosity of solution, and the hydrodynamic radius, or the hydrated radius of the analyte. Okay, so what does this mean? For analytes of the same charge, as you get a decrease in size, so if we have same charge, but we are lowering the size, lowering the radius, that means we lower the radius, we're going to lower this frictional coefficient, and we increase the electrophoretic velocity. Okay, so they're going to move faster if they're smaller in size. Similarly, if our size is the same and we increase the charge, they're going to move faster. Okay, so this is our basis for separation is going to be twofold, first on charge, then on size. Okay, so and remember that they're being pulled in opposite directions. Positives are going to separate one way, the negatives in the other. Now, if we wanted to create a flow that's going to push everything towards one end, that would help us get everything to come out on one side, and we would only need one detector. I think of this kind of like being in one of those lazy rivers. Okay, you can flow with the current headed toward the cathode, or you can flow away from the current headed toward the anode. But eventually, if the current is strong enough, even if you're swimming against the current, you're going to end up moving towards the same end as everyone swimming with the current. It just is going to take you longer because you're pushing against the current. So if we kind of put a current here that's kind of overlaid over, so that there's a current in the solution that's pushing everything toward the cathode, that can overpower our anions and push them towards the cathode, we might actually get movement all in the same direction. Now, this solution current is going to be added onto our cations here, and so those are going to move super fast, right? They're going to move even faster towards the cathode, and eventually the anions would be pushed there as well. Okay, so we're going to overlay some kind of a current in the solution to push everything that way, like a physical moving of the solution. So how do we want to do that? Okay, so there's a couple things that are going to go on here. We're going to use electroosmosis to get this current to go. Electroosmosis. Okay, so let me sketch out what electroosmosis is doing here. Now, we're going to put this solution into a capillary. Okay, so a capillary is a very small, very thin diameter of tubing, so much so that if you looked at it, you would think it's just a wire, but it's actually a very thin piece of tubing. Okay, so we get our fused silica tubing here that has a very narrow inner diameter. And if you remember from some of our other discussions, silica has those OH groups, and so at an appropriate pH of greater than 3, we actually get negative groups on the surface. Okay, so our silica actually has these little negative charge groups on the surface, and I'm kind of drawing them, sticking them in just so we can see how this works. These are right up against the edge. Remember, this tube is pretty narrow, so there's not a whole lot of an inner diameter here. I'll draw one more. All right, so those are our little negatively charged groups on the surface. But we know that negative charges do not exist in a vacuum. There is always a counter charge because it has to be a net neutral. Okay, so these are my little counter ions that are just stabilizing these negatively charged groups on the surface. So these are counter ions. And the composition of these counter ions doesn't particularly matter. It's often H+, but it doesn't particularly matter what they are. But they're little positively charged groups, okay? So what happens here? Now we have our anode at one end. That's positively charged. We have our cathode placed at the other end of the tube, and that's negatively charged. Now when I apply the same electric field, notice I haven't even put any analytes in here, but just even without analytes, I've applied my electric field to this, and what's going to happen is you're going to get all of these counter ions here to start moving towards the cathode. Okay, so these are all going to start moving because they're still positively charged, and while they're counter ions for these negatively charged surface groups, they are still mobile. They're not covalently linked and bound like the negative charges are to the surface. Those are bound. They're not going anywhere. They are immobilized. But the counterbalance ions are not. So those counter ions can start moving, and what that does is it creates a flow along the edges of the capillary that effectively is moving towards the cathode. Now, these capillaries are so narrow that as they move towards the cathode, they're actually drawing a full current. There's enough of this movement, and it's a narrow enough tubing that it's going to pull a net effect of giving you an electroosmotic flow towards the cathode. So then this flow has that similar effect on the analytes in solution. So if I have a positively charged analyte here in green, it's going to naturally have a positive or a draw towards the cathode because of the difference in charge there, but then it's also going to have a pull from the electroosmotic flow. So for cathodes, their electrophoretic velocity is going to add to the electroosmotic velocity, and you get them moving extra fast, okay? Now for something like an anion that has a negative charge, okay, that's going to be naturally pulled towards the anode, but it's going to have that overall pull backwards towards the cathode due to the electroosmotic velocity of the solution. So here they're going to start canceling each other out, and as long as the electroosmotic velocity is higher than the electrophoretic velocity moving towards the anode, it will eventually end up at the cathode. Okay, so in this case now we can put a detector in front of the cathode, and our cations are going to hit the detector first, and our anions will eventually come out behind them, with the anions that are pulled the least strongly towards the anode coming out at the cathode first because they're not swimming upstream quite as hard as ones that are being very strongly pulled. Okay, so let's put up some notation for our electroosmotic velocity. So we talk about UEO as opposed to UEP. UEP was our electrophoretic mobility. UEO is going to be our electroosmotic mobility. Electroosmotic mobility or velocity. Put velocity here. Okay. And we're going to say that equals mu EO. This is our electrophoretic mobility. Times our electric field strength. So the stronger the electric field is here, the stronger this velocity is going to be. Okay? So some things that can play a role in the velocity is going to be based on the distance from the injector to the detector. They might pick up less speed. And then also we need to consider kind of the time for a neutral that is only getting electroosmotic velocity. Okay. So as you consider what order things are going to be moving in capillary electrophoresis and what order they're going to elute in, remember that you have to first consider their charge and the hydrodynamic radius, because that's going to dictate their strength of their pull towards the anode or the cathode. Then you have to consider how electroosmosis plays a role, and how then your analytes that are pulled towards the anode are going to be pushed backward, but the ones pulled more strongly to the anode are going to be the last ones to elute, because they're going to be swimming upstream the hardest. Okay, so that's the basis of capillary electrophoresis, and our result from the detector is simply going to look at the current over time. So it's going to look very similar to a chromatogram, except again you've got a current rather than as your detector. Okay. This is not called a chromatogram because, again, we're not doing chromatography. This is instead called an electrophoregram. And you might hear this term a lot in doing protein analysis or DNA analysis, because those are biological materials that are naturally charged. And so these kind of ion separations are really useful for proteins, peptides, and DNA molecules.